All right. Yes. Yesterday's recording on? No, it's right. All right, this is 8.22, Rotational Dynamics. We're going to finish up 8.2. We have one more section on this called Equilibrium, 8.3, which will be, I believe, Monday. So today we're going to calculate the moment of inertia, and we're going to calculate torque using this moment of inertia. So, moments of inertia. Inertia is kind of like a resistance to motion, or like remember Newton's first law is inertia. Mass is going to continue doing what it wants to be doing. So, moment of inertia is kind of like once you get that mass going, it's kind of like a resistance almost to motion. It's hard to describe, but we're going to talk about moment of inertia in rotation. That's what it's to. So, for instance, I have this lovely meter stick here, which is my weapon, right? It's a weapon.
It's funny because right when you picked it up, he was like, "I feel threatened."
Oh, that's good. Okay, well, I have this meter stick, and when I hold it at the center, you can see I can actually move it pretty fast, right? And it's because the moment of inertia, the rotation is around the center of it. And on the sides of it, I have pretty much split so that its mass is half on this side, half on this side. So I can move it pretty quickly. So I can hit you lots of times. Right? Really fast. Now, if I hold it more like a sword, you can see that all of its moment of inertia, or all of its mass, is on the outside of the pivot, on one side of it. So it takes me a lot more force to get it to go. So its resistance to motion, its moment of inertia, is much larger. This means that I can't hit you a bunch of times really fast, but I can hit you pretty hard. So with this particular weapon, it's a trade-off between speed and force. So do I want to do a lot of damage, or do I want to hit you a bunch of times?
A lot of damage.
It depends. It depends.
Are you trying to kill them, or are you trying to injure them?
I think it depends on who you're fighting. Right? If you know, whatever. You guys deal with this every day in your computer games, right?
Do we?
Computer.
It's a trade-off between damage and speed.
Why not both?
Why not both? You can't build just straight damage. All right, so this particular equation is not the moment of inertia for all things. This particular equation is it's a general mode of inertia, and that's more like an object on a circular path. So like this stopper. This stopper is spinning on a circular mass. And if you want, you could think of it as a mace if you're really stuck into weapons right now. Or like the Earth around the orbit of the Sun, you would use I equals mr squared. But for this object, you are not going to use I equals mr squared because we know that at the center, it has less moment of inertia than if I move it on the end. So there's got to be different equations for different things depending on how they're moving. And I'll show you the table for that. It's also in your book. This moment of inertia I is measured in kilograms meters squared, where your mass is going to be the mass of the whole object, and the R will be basically the distance. Now, when we use these equations, we actually use the whole length of the thing, but most of the objects, for instance, like this, it would be the radius of the string from the end of the stopper to the top of my little handle here. Now, you're going to be using these next week to swing around and find the weight of these things. Sounds like very exciting, right? You guys do not look excited today. What's wrong with you?
It's Friday, right?
You should be excited because you get to leave, right?
Party.
Okay, I see all blue cups, so let's move on. This is the table. No? You had a red cup. Okay. This is a table that's in your book. You do not need to write it down, but if you have a camera, you might want to take a picture of it because it might be easier to read the one in the book. That's up to you. You can see that depending on the different objects. Take a picture quietly. Depending on the different objects, you're going to have different equations. So a hoop, the top one up there, is the same as something spinning on a circle like our little star. And that's basically because the mass is all on the outside, so it's going to have the same moment of inertia equation.
What page is this on?
206. Thank you. It's almost gone. All right. Now you can see that if the mass is distributed evenly throughout this whole disk, we've changed it to 1/2 mR squared. That's because the mass is not all on the outside. So this one's actually going to be easier to slow down than this one because it has less of a moment of inertia. This is the equation for a sphere, 2 fifths mR squared. And then here is what I'm swinging around here, my meter stick, right? If I go through the center, it's only 1/12 mL squared, where the same object, if I swing it at the end, is 1/3 mL squared. So it actually has a higher moment of inertia. That's where you have higher force and thus lower speed. All right, and then the last one here is a rectangular plate that has 1/12 mL squared plus W squared. I almost said omega. And that's like this thing, if I were to spin it, try and find its moment of inertia. If it was rotating about the center. You guys want to share? No? All right, so the moment of inertia depends on the shape of an object. You can use the table, which is in your book, apparently on 206, to find the different moment of inertia. So depending on your object, it could be like a tire or a bicycle wheel or a pulley. Any of those things, you want to use the moment of inertia that works best for that object. So here is a practice for us. What's the moment of inertia of a rectangular metal plate? Has a length of 30 centimeters and a width of 25 centimeters, and it has a mass of 5 kilograms. So, go through here, we have 30 centimeters. Try that again. 30 centimeters, 25 centimeters, 5 kilograms. What's the 30 centimeters? Length. What's the 25 centimeters? And what's the mass? Sorry, what's the 5 kilograms? Mass is mass, right? What are we looking for?
Moment of inertia.
Moment of inertia. Good. Now, what's the equation for this moment of inertia?
I equals mR squared or cubed. Squared or what? Squared.
What is it? What is the object? What's this object?
Oh.
Okay, so now what's the equation? 1/12 m L squared plus omega squared, or W squared, right? Okay, so you have to make sure that you're picking the right equation for the object. You can't just use mR squared for everything.
Wait, why do you add the plus the squared?
It's part of the equation.
Oh, so the mR squared is only for like.
A hoop or a circular object, like things going on circular object.
Do we have to convert to meters?
Yes, you do have to convert to meters. So, what is L in meters? 0.3. And what about W in meters? 0.25 in meters. Good. Okay, so this is going to be I equals 1/12 times 5 L squared plus W squared, 0.25.
Let me get my calculator.
And I have 0.0635, and this is kilograms meters squared.
So like this whole unit just a matter of remembering the equations.
It's not even like remembering equations because you can write the equations down and have them on the test. It's more like there are so many equations, which equation are you going to use? That is probably the problem. Probably. I can think of a few more problems you could have. Okay, so any questions on this? I see 2 red cups. Okay. Now this moment of inertia is also going to help you around, like when you toss something, how is it going to spin? And it's always going to spin around the center of mass. So to find the center of mass, what you want to do is take your object and hang it. And it's going to hang, down. So if you have a string, draw a straight line down, straight down, and then pick another point to hang it from. So let's say here. And draw a straight line down. Wherever those two lines intersect, that's going to be your center of mass. So if I grew that thing, it's going to rotate around that center of mass. So for instance, if you throw a wrench, where the wrench has a center of mass closer to the head of the wrench, you can see that it's still rotating, but it's rotating around this center of mass. And that center of mass is thrown in a straight line. So even though it's rotating, the center is on straight. Isn't that neat?
Well, what happens if you throw it? No, I guess.
Yeah, it doesn't matter how you
throw it. It's gonna go like this. You can do it on its side.
Then it'll do it around that direction. Any more questions on that one? No? Kind of neat? Okay, so I want you to write down this equation, torque equals I alpha. This is Newton's second law in rotational motion. I'm going to write a little table up here. It's not that important, but it's kind of interesting, so you're welcome to write it down. We're going to go linear and angular. Okay, so in linear we have angular, not angular. Linear we have displacement, velocity, acceleration, force, and mass. Look good? In angular, we have angular displacement, angular velocity, angular acceleration, torque, which is angular force, and mass, which is going to be moment of inertia, so angular mass. Right? You guys starting to see the connection? So this is all linear stuff, and that's all angular stuff. They're the same stuff, right? They're the same ideas, but this one is rotating. Another little interesting thing we'll put here might be helpful for your homework, at least when you're trying to figure out which variable it is. This is meters. This is radians. Meters per second, radians per second. Radians per second squared. Nope, that one's wrong. Sorry. Meters per second squared and radians per second squared. This is newtons, Newton meters, and this one is kilograms. This one's kilograms meters squared. So a little weird on that one, but. So when you have, on this one, F equals MA, you're going to have on this side, torque equals I alpha. That's good.
I do that with high five people. We're just high fiving before you go to it. Quiet. You're like a loser if you No, the first time. How do you pronounce
I got
Tau? On the angular and third down.
Tau.
And then the T.
Oh, okay. Here, this is theta,
Theta. Omega.
omega, alpha,
Alpha.
alpha. Your fish's name is Alpha now.
Alpha.
Tau,
Tau.
and then that's just I.
Tau. Wait, the W is the name is beta?
Omega. Alpha, omega.
I don't like slang.
All right, see one red cup?
Guys, I'm not illiterate. Isn't that right, Olivia? Okay, yeah. See? Yeah, Davis cup. Oh, it's on the board. Duh. This is terrible work. Did she show you that word crying video? It's like, you know the song Blurred Lines? It's like a remake about how people are illiterate. And it is hilarious.
All right, we are going to do this practice problem. It is not a clicker question, so don't try to put in your clicker because it's not going to work. Now, this is a basic moment of inertia torque type problem. It uses 4 equations, so that's why it's hard. So let's look at it. We have a pulley with a mass of 0.4 kilograms. It holds a basket of apples at 1.1 centimeters from the center of the pulley. What's the angular acceleration of the pulley? So what's this 0.4 kilograms? What is the 1.1 centimeters? Radius. And what are we looking for?
Angular acceleration.
Which is?
Torque.
Alpha. Alpha. There we go.
It's not.
All right, it's alpha. Okay, let's draw a picture. We have some sort of radius here, and we have the basket of apples going down this direction. So basically, this is our force. So we have some sort of force. Let's start listing some equations that we can apply to this. Nobody has any equations that we can apply to this.
Oh.
That's kind of sad.
Is it this one?
I got it.
No. We're looking for fish.
I got it.
Which equation for torque?
One.
Okay, so one of them, the torque with force in it, FR sine theta, right?
Or MR squared, right?
Uh,
Oh, no, because you're not
say
looking
that again?
for I equals MR.
This one is a pulley, which is actually a solid disc. So let's look at our I.
1/2 MR squared.
1/2 mr squared. Good. I equals 1/2 mr squared. Good. Okay, now what else are we going to use? That gives us torque. That gives us I. Remember, you're looking for alpha.
What's the unit for alpha? Is there one? Acceleration equals radius alpha.
That one you're pointing at on the board.
Torque equals I alpha. All right. Now we need one more.
F equals MA.
Close. F equals
MR squared. MA.
mg. The weight. It is A. It's just we need to be specific at mg. All right. These 4 equations will get you to the answer. You can either, like me, be a cheater and say, all right, I'm going to put this one in here. So this will be basically mg r sine theta, and then I'm going to put the torque in here, and I'm going to put this equation in here and come up with one big equation. So I only have to put things into one. Some people don't like that, so I'll do it. I'll show you what the equation is. Mg r sine theta equals 1/2 mr squared alpha. So you can see here that actually your m's go away. So that's one way, and this r is going to simplify. So that's one way to do it. You don't have to do it that way. It's okay. I'll do it step by step with you. Let's find the weight of this thing first. So F equals mass times gravity. Somebody's got to do some calculations for me.
Oh,Ll do it.
3.92.
Whatever.
3.92 newtons. All right. We can do the torque one next. Torque is going to be 3.92 newtons times, what's wrong with this radius here?
Centimeters.
It's in centimeters, so we need to put it in meters. Okay, so this is 0.011 sine. What's our angle?
It's
90 degrees.
90 degrees. Good. Remember, when it doesn't give it to you, it's pretty much going to be 90 degrees. So what's the torque then?
0.04312. So 0.04.
We'll do that. That's fine. Newton meters. Okay, so we found torque. Now let's find I, moment of inertia. 1/2, 0.4, 0.011 squared. So what's I?
I'm getting there. Really small.
Really small. Is it 2.42 times 10 to the negative 5?
It is.
Okay. Kilograms meters squared. Now what?
Now we put it in the fishy one, right?
The fishy one, right? Okay. Torque equals I alpha. So torque 0.0431 equals 2.42 times 10 to the negative 5 times alpha. What is alpha?
Wait, 2.24, 2.42.
Whatever you got. Because that's from memory. That might be wrong.
1780.99. So 1781. A little big.
It's fine. I mean, yes, it's very large, but that's because my numbers are weird.
So I'm not wrong.
No, you're not. Okay. All right. Any questions on that? Can you see why this is hard?
What?
Yeah, I do.
It's just because there's like so many equations to choose from.
And is every problem going to have multiple equations?
I think this is probably the hardest problem you will encounter.
Oh.
There is another one. I don't remember if it's in this homework or the review, but it has two apples, one on this side and one on this side. So you'd find the torque of this one and the torque of this one. This one's going to be positive. The other one would be negative. You add the torque right here.
You just add the other one?
You just add them together and then you plug it into the equation. Okay, so I have like 2 clicker questions for you, and then you'll have the rest of the time to start your homework. Or cry, whatever. So let me just end this.